But I'll move on and just leave up my summary slide. And I'm a minute late. Sorry for that.
So we have time for just a few questions. Yeah, Javi.
So of course one has to keep in mind that the star formation efficiency is small, usually like 10%. So you have a lot of gas, much more mass in gas than in stars to feed the black holes.
Mm-hmm.
And indeed, I mean, quasars do show 10 solar masses per year typical accretion rate. So you really need every month or so a star in order to compete with the gas accretion.
Yeah. Yeah.
But maybe the strongest flare, super Eddington accretion, occurs as a result of TDs, because you definitely get super Eddington mass infall during the disruption of a star,
Yeah.
which you don't get in the standard accretion disks.
Yeah, no, that's good.
And the other thing is, of course, the friction. The question is, you don't take into account the friction on the gas of the stars.
Mm-hmm.
That could play a role as well in grinding the orbits and bringing the stars into the black hole.
Yes. Right now I've only dealt with gravity as if like the disk is perfectly formed and then wants to equilibrate. But yeah, there should be leftover gas.
And that would bring the stars in.
Yeah, yeah, that's true.
Yeah.
Maybe this is related to your mass segregation comment. If it isn't, you can talk about that anyway. But I'm curious if this eccentric disk tidal disruption scenario selects for a certain part of the stellar mass function. Are you disrupting a certain type of star, preferably? Or?
Thank you, yes. It does relate to mass segregation. So what we thought before we ran some simulations, which is like different mass stars in the disk, is that the most massive objects would want to radially migrate inwards, and the inner edges of the disk are the most eccentric parts of the disk, so you might pump up the tidal disruption event rate that way. And what we found was the radial mass segregation rate was not that strong at all, and yet the more massive stars wanted to tidally disrupt. So we're like, why? What are they doing? And we weren't even changing the tidal disruption radius. It was independent of mass in our simulations, everything very simple. So we're just like, what are we doing here? And what it turns out is that it's vertical mass segregation. So the inclination distribution of the most massive objects is smaller. They're more likely to be in the midplane of the disk. And when you're in the midplane, the torques acting on you want to change your eccentricity rather than change your orientation. And so these massive stars are more likely to go to really high eccentricities and be tidally disrupted. Of course, the more massive stars won't last as long as the other stars. So this is something we're trying to think through. What happens after your more massive stars turn off the main sequence? And they're all stellar black holes and neutron stars and things like that. Are they producing a lot of gravitational wave bursts? So we kind of expanding from that part. But you wouldn't expect you wouldn't expect the same stars to be tidally disrupting as when you have two-body relaxation in a star cluster. It preferentially picks out the more massive ones.
Okay. Back there.
I'll ask, I guess, the same question, but for the inclination instability. Do you run these simulations with a mass spectrum, and does it have any implication for say, the primordial Kuiper Belt mass distribution?
So I'm giving a talk in 25 minutes. That's not talking about how the inclination instability changes, but talking about the differences in mass and secular dynamics, and it leads into dinosaurs. So it was a natural next step in the project to be like, and I gave it to an undergrad, kind of like, let's just change the masses and see what happens. The inclination distribution does change, like the more massive objects go to a lower inclination, and the less massive objects reach higher inclinations, but we don't think that's going to be very important in the solar system because of timescale reasons, how long it takes to actually segregate like that. But it is something that we've been looking at.
Okay. Last question.
Okay, so in the stable disks, does it matter to the disk that orbits that are preferentially deleted by interaction with the black hole are always kind of like the eccentric leading ones rather than the circular trailing ones? Does it matter? Does that asymmetry matter?
So there's two quick...
Do I even have that right?
Yeah, so there's two quick. So the first thing is, it's not always the leading ones.
Okay.
Because we're in the full loss cone regime, just to kind of quickly throw that out, meaning that you can get really eccentric really quickly and actually flip your inclination. if you don't get tidally disrupted. You just go like right through, your angular momentum vector just flips. So then you go back across the disk, and you have a second time that you can tidally disrupt, because the torque's reverse. So this is why we get peaks at 0 inclination with respect to the disk and 180. So they're not perfectly matched. There's still more chance you'll get tidally disrupted at 0 inclination, but there is actually more of a balance than you would expect.
That's really interesting.
Yeah. So, but otherwise, like, does it matter? Like for stability,
More
or
for like the long-term evolution of this disk, like.
not in ways that I've seen or I've kind of thought out that it should matter. But there is also the fact that you also delete orbits on the other side of the disk too.
Yeah.
Just
So it's
opposite.
more symmetric than I was
Yeah.
imagining.
Well, thanks everybody for showing up. Let's thank our speakers.
Yeah, I guess
Thank
I
you.
still come from that side.
This is my last trip abroad, early April.